Every moment of every day, the ground beneath your feet is moving. Not enough to shake buildings, not enough to wake sleeping cities, but Earth is never completely still. Oceans push against coastlines, wind transfers energy across continents. Deep beneath the crust, tectonic plates shift with almost unimaginable slowness. To human senses, the planet feels solid and silent. In reality, it behaves more like a gigantic instrument constantly humming in the background. And hidden inside that endless vibration, scientists discovered something deeply unusual. A pulse. Every 26 seconds, not randomly, not once in a while. Repeated with such consistency that researchers around the world kept encountering the same strange rhythm inside seismic recordings. Imagine hearing a faint knock somewhere inside a massive building. One knock, then another. Always separated by the exact same interval. At first you might ignore it, but after hearing it again and again for decades, the question becomes unavoidable. What exactly is making the sound? This phenomenon is known scientifically as a microseism, a tiny vibration traveling through Earth's crust. Outside scientific circles, however, many people now call it something far more memorable: Earth's heartbeat. Scientifically speaking, the nickname is misleading. Earth is not alive in the biological sense. It has no heart, no circulation, no nervous system. But psychologically, the comparison is understandable. Human beings instinctively connect rhythm with life. A heartbeat is one of the first patterns we ever learn to recognize. Even before birth, the human brain becomes familiar with steady internal rhythms. So when people hear that our planet produces a repeating pulse every 26 seconds, the idea immediately feels strange, intimate, and slightly unsettling. The story began in 1962. At Columbia University's Lamont Doherty Earth Observatory, geologist Jack Oliver was studying seismic data recorded by instruments designed to monitor earthquakes. Most of the information collected by these machines looked chaotic. Tiny vibrations from storms, waves, distant quakes, industrial activity, and shifting crust all blended together into what researchers often considered background noise. But Oliver noticed something hidden beneath that noise. A weak signal repeating every 26 seconds. The timing was precise enough to stand out. Now, this is where scientific thinking becomes interesting. A single strange reading rarely means much. Instruments fail, data becomes contaminated, local disturbances create false patterns all the time. But repetition changes everything. If a signal survives across years, across continents, and across different generations of equipment, scientists can no longer dismiss it casually. And this signal refused to disappear. Year after year, the pulse continued showing up. Meanwhile, Earth science itself was entering a revolutionary period. Researchers were uncovering the mechanics of plate tectonics, proving continental drift, and reshaping humanity's understanding of the planet. Compared to discoveries that explained entire mountain ranges and ocean basins, a faint 26-second vibration seemed minor, so the mystery remained mostly in the background. Quiet, persistent, waiting. What makes the story remarkable today is the contrast between scientific power and scientific uncertainty. Modern instruments can detect gravitational waves produced by collisions between black holes billions of light years away. Scientists can image atoms, map distant planets, and analyze radiation from the early universe. Yet somewhere beneath the Atlantic Ocean, Earth continues producing a repeating seismic rhythm that nobody has fully explained. And perhaps the most fascinating part is this. The pulse is happening right now, while cities sleep, while airplanes cross oceans, while millions of people move through their daily lives completely unaware that the planet beneath them keeps time with mechanical precision. The obvious question soon became impossible to ignore. How can an entire planet develop a rhythm, and why does it repeat every 26 seconds? As scientists continued listening more carefully, the mystery only deepened. As the years passed, the pulse continued, quietly, almost stubbornly. While Earth science evolved through satellites, supercomputers, and digital modeling, the strange 26-second rhythm kept appearing in seismic records like an unanswered message buried beneath the planet's surface. What makes this stage of the story fascinating is not only the mystery itself, but how close science came to overlooking it completely. For decades, the signal remained largely ignored, Not because researchers were careless, but because science operates through priorities. During the late 20th century, seismologists were focused on earthquakes, tectonic boundaries, volcanic systems, and nuclear monitoring. Compared to those enormous scientific questions, a faint repeating vibration seemed like background clutter. But science has an interesting habit. Sometimes old mysteries wait patiently for new technology. That turning point arrived in 2005. At the University of Colorado, graduate student Greg Benson was working with seismic software designed to isolate weak signals hidden beneath stronger geological noise. In simple terms, he was trying to clean the data. Imagine standing inside a crowded room where hundreds of conversations overlap at once. Now imagine trying to isolate a single whisper from the far corner. That is essentially what modern seismic filtering attempts to do. And while testing the system, Benson found the whisper. The 26-second pulse emerged again with extraordinary clarity. Not distorted, not fading, still repeating with the same eerie consistency first noticed by Jack Oliver decades earlier. Now, the mystery became much more serious, because the new instruments were vastly more advanced than those used in the 1960s. Seismic sensors had become more sensitive. Computer analysis had improved dramatically. Digital networks could compare signals from stations spread across entire continents. Yet despite all that technological progress, the pulse remained unchanged. A teaching insight is important here. In science, stable patterns often indicate stable mechanisms. If a phenomenon repeats consistently across long periods, researchers begin looking for systems capable of maintaining that precision naturally. And nature is usually messy. Ocean storms vary, wind patterns shift, earthquakes occur unpredictably. But this signal behaved almost mechanically. Benson and his advisor, seismologist Mike Ritzwaller, decided to investigate further. Using triangulation methods, researchers compared how the signal arrived at different seismic stations around the world. Much like GPS calculates location through timing differences, scientists could estimate where the pulse originated by measuring how seismic waves traveled across Earth. The results narrowed the source to a region in the Gulf of Guinea, off the western coast of Africa. More specifically, near the Bight of Bonny, close to Cameroon, Nigeria, and Equatorial Guinea. That discovery changed the mystery completely. Until then, the pulse could still have been dismissed as scattered environmental noise drifting unpredictably across oceans. But now researchers realized something extraordinary. The signal was coming from one fixed location, every 26 seconds, year after year. Imagine hearing the same distant drumbeat from the exact same point on Earth continuously for decades. At that scale, coincidence becomes difficult to accept. Even more surprising was the reach of the signal. The pulse was not confined to West Africa. Seismic stations thousands of kilometers away could still detect it. The vibrations traveled across continents and oceans, threading themselves into the background motion of the entire planet. That meant whatever generated the pulse was not a small local disturbance. It was interacting with Earth on a planetary scale. And now, a new question emerged. If the signal came from a fixed point in the Gulf of Guinea, what physical process could possibly maintain such perfect timing for decades? To answer that, scientists turned toward the most powerful force shaping the region: the ocean. The moment researchers traced the signal to the Gulf of Guinea, attention shifted toward the most obvious force capable of shaping that region continuously: the Atlantic Ocean. At first glance, the explanation sounded surprisingly reasonable. The ocean is not calm in the geological sense people often imagine. Even when the surface appears peaceful, enormous amounts of energy are moving through water constantly. Long ocean swells generated by distant storms can travel thousands of kilometers across entire basins. In some cases, waves born near Antarctica eventually reach the western coast of Africa days later. That detail matters, because scientists began wondering whether those waves were interacting with the seafloor in a very unusual way. To understand the theory, imagine pushing water repeatedly against the side of a bathtub. The force transfers into the structure itself. Scaled up to planetary dimensions, powerful ocean swells can slightly deform the seafloor when they strike continental shelves and shallow underwater regions. Those deformations generate vibrations, and vibrations travel efficiently through solid rock. This process is known as microseismic noise. In fact, Earth's oceans constantly generate low-frequency seismic signals. Seismologists detect them all the time. In a sense, storms at sea can make the entire planet ring very faintly, almost like tapping a bell with soft fingertips. But the Gulf of Guinea appeared different. Researchers noticed that the region possesses unusually favorable geography for resonance. The coastline curves inward. The continental shelf changes depth in a distinctive way. Under certain conditions, incoming swells could theoretically bounce, overlap, and reinforce one another instead of dispersing randomly. A teaching insight helps here. Resonance occurs when energy repeatedly arrives at exactly the right timing to amplify motion. A child on a swing demonstrates the principle perfectly. Push at random intervals and the motion weakens. Push rhythmically at the correct moment and the swing rises higher, with surprisingly little effort. Scientists suspected something similar might be happening beneath the Atlantic. Ocean waves could be feeding energy into the Gulf of Guinea with enough consistency to generate a repeating seismic pulse. Some researchers compared the phenomenon to blowing across the opening of a bottle. Air itself does not create the sound directly. Instead, it excites resonance inside the bottle, producing a stable tone. Under this theory, the Gulf of Guinea functions like a gigantic natural resonating chamber. The idea explains several important observations immediately. First, it explained why the signal originated from one fixed location. Second, it explained why the pulse persisted for decades. And third, it showed how ocean energy could generate vibrations strong enough to travel across continents. For a time, the theory appeared promising. But science becomes most interesting when explanations almost work, because almost forces researchers to examine what still does not fit. And several details refuse to cooperate. The largest problem involved consistency. Ocean conditions are constantly changing. Storm systems strengthen and weaken. Seasonal wind patterns shift. Swell direction varies throughout the year. If ocean waves alone produced the 26-second pulse, researchers expected the rhythm itself to fluctuate significantly. Instead, the signal remained strangely stable, almost too stable. Another issue involved geography. There are many coastlines around the world with continental shelves, curved basins, and strong wave activity. Yet no other region produces a pulse matching the same combination of precision, strength, and persistence. That raised an uncomfortable possibility. Perhaps the ocean was only part of the story. Fun fact, some seismic stations located far inland, hundreds of kilometers away from coastlines, still regularly detect vibrations originally generated by ocean activity. The planet is far more interconnected mechanically than human senses would ever suggest. Even so, the deeper scientists examined the Gulf of Guinea, the clearer it became that normal ocean behavior alone could not fully explain the mystery. Something else might be contributing beneath the surface, and that possibility led researchers toward another force capable of producing rhythmic geological activity: volcanism. If the ocean theory explained part of the mystery, researchers still faced one major problem. The pulse was too stable. Ocean systems constantly change. Storms shift direction, waves rise and collapse, wind patterns vary throughout the year, yet the 26-second signal repeated with remarkable precision, almost as though some hidden mechanism beneath the Atlantic was regulating it. That possibility pushed scientists toward another explanation: volcanic activity. In 2013, Chinese seismologist Yingjie Xia proposed that the source might originate from geological activity beneath the Gulf of Guinea rather than from the ocean alone. The idea gained attention because near the estimated source lies Sao Tome, a volcanic island formed through deep tectonic processes. The island sits along the Cameroon volcanic line, a region shaped by ancient magma movement beneath Africa and the Atlantic. In simple terms, the area was already geologically active. Inside volcanic systems, magma pushes through underground fractures under enormous pressure. Chambers expand and contract. Heated fluids move through cracks deep within the crust. These processes generate vibrations. Scientists already observe repeating seismic signals near active volcanoes around the world. Some are called harmonic tremors, rhythmic waves caused by moving magma and pressurized fluids. A useful comparison is a musical instrument. When air moves through a flute, vibration creates a stable tone. Researchers wondered whether underground geological pathways could behave similarly beneath the Atlantic. The volcanic hypothesis explained several observations effectively. It explained the fixed location. It explained the long-term persistence. And it connected the pulse directly to a known geological structure. But the theory encountered serious limitations. Volcanic systems are usually irregular. Pressure changes constantly underground. Pathways shift. Energy fluctuates. The 26-second pulse did not behave that way. Its rhythm remained unusually clean and stable. There was another problem. Most volcanic seismic signals weaken rapidly with distance, but the Gulf of Guinea pulse had been detected thousands of kilometers away, including in North America and Madagascar. That level of reach suggested something much larger than an ordinary volcanic tremor. A teaching insight becomes important here. In science, a strong theory must explain all major observations at once. One theory cannot explain location while another explains timing. The best explanation must account for the entire pattern. And this mystery resisted simplicity. The ocean theory explained large-scale energy transfer. The volcanic theory explained the fixed source. Neither fully explained the precision. Fun fact: scientists can sometimes detect underground magma movement weeks before eruptions occur simply by analyzing subtle seismic vibrations. Yet the 26-second pulse still behaved unlike ordinary volcanic activity. As a result, the scientific community remained divided. Some researchers favored ocean resonance. Others favored volcanic processes. A few suspected both mechanisms might interact together beneath the Atlantic, but no explanation solved every piece of the puzzle. Meanwhile, every 26 seconds the pulse continued, quiet, precise, and completely invisible to human senses. What made the 26-second pulse even stranger was the fact that nobody could feel it. A ship could pass directly above the suspected source region without passengers noticing anything unusual. The ocean would appear normal, the air would remain calm, no rhythmic shaking would move through the deck. The signal existed entirely outside ordinary human perception. Only instruments could detect it. That detail reveals something important about the planet itself. Human senses evolved to survive everyday environments, not to measure microscopic geological motion. Compared to scientific instruments, our perception is extremely limited. Modern seismometers can detect movements smaller than the width of a human hair. Some are so sensitive they can record distant ocean storms occurring thousands of kilometers away. And once scientists began listening carefully, they discovered something remarkable. Earth is constantly vibrating, not occasionally. Constantly. To most people, the ground feels stable and silent. In reality, the planet behaves more like a giant system filled with overlapping frequencies moving through rock, water, and atmosphere at all times. Storms generate low-frequency tremors. Ocean tides flex Earth's crust. Tectonic plates grind slowly beneath continents. Even powerful winds transferring energy across mountain ranges can create measurable seismic vibrations. A useful teaching comparison is a crowded orchestra warming up before a performance. Hundreds of different sounds overlap simultaneously. No single instrument dominates completely. Yet hidden inside that mixture, trained listeners can isolate specific tones. Seismologists study Earth in a very similar way. Within the planet's constant background motion, the 26-second pulse stood apart because of its unusual regularity. Researchers have identified other repeating microseismic rhythms near Antarctica and New Zealand, but none display the same combination of precision, persistence, and global detectability observed in the Gulf of Guinea. As far as current evidence suggests, this signal may be unique, and uniqueness in geology is rare. Fun fact: large earthquakes can cause Earth to vibrate like a bell for days. After major seismic events, sensitive instruments sometimes detect oscillations traveling repeatedly through the planet before slowly fading away. But unlike earthquakes, the 26-second pulse does not require a catastrophic event. It simply continues, quietly, every 26 seconds. That persistence gradually changed how scientists viewed microseismic activity itself. For many years, researchers treated background seismic vibrations as interference, something to remove while searching for earthquakes and major geological events. But eventually, scientists realized the noise itself contained valuable information. Earth's vibrations were not meaningless static, they were data. Every tiny movement traveling through the crust carried clues about the structure of the planet beneath our feet. And among all known signals, the mysterious pulse from the Gulf of Guinea became especially important because of one key advantage: consistency. Unlike earthquakes, which occur unpredictably, the pulse repeated continuously, again and again and again. That meant researchers potentially had access to a natural seismic source operating with mechanical regularity, a signal that could help scientists study Earth's interior in entirely new ways. But there was still one major obstacle. Before researchers could fully use the pulse as a scientific tool, they first needed to answer a far more difficult question. What exactly was generating it? The realization changed modern seismology in a profound way. For decades, researchers treated background seismic vibrations as interference. When scientists searched for earthquakes or major tectonic events, weak ambient motion was considered noise to remove from the data. But during the early 2000s, a different idea emerged. What if the noise itself contained useful information? That question transformed an entire field of Earth science. Researchers discovered that tiny vibrations traveling continuously through the planet could reveal hidden structures deep beneath the surface. By measuring how seismic waves move through different rock layers, scientists could construct detailed underground maps without waiting for earthquakes to occur. The technique became known as ambient noise tomography. The name sounds technical, but the underlying idea is surprisingly simple. Imagine a doctor using ultrasound to study organs inside the human body. Sound waves pass through tissue, and the returning signals reveal internal structures. Seismologists realized Earth could be studied in a similar way, except instead of artificial sound waves, the planet already produced its own constant vibrations naturally. Ocean waves, storms, tectonic movement, and atmospheric activity continuously generated seismic energy. Researchers only needed to measure how those vibrations traveled through Earth's interior. In a sense, the planet had been creating its own scan data all along. A teaching insight is useful here. Different materials affect wave motion differently. Seismic waves travel faster through dense solid rock and slower through softer or partially molten regions. By comparing arrival times at different instruments, scientists can infer what exists underground without physically seeing it. This transformed microseisms from scientific annoyance into scientific tools. And among all known microseismic signals, the 26-second pulse became especially valuable. Because unlike earthquakes, it never seemed to stop. Earthquakes are unpredictable. They release enormous energy briefly and then disappear. The Gulf of Guinea pulse behaved differently. Every 26 seconds, another wave emerged. Again, and again, and again. That consistency gave researchers something extremely rare in geology: a continuous natural seismic source. Fun fact: some modern seismic studies use vibrations from ocean waves and even human traffic to map underground structures beneath cities. Tiny background motions invisible to people can still reveal valuable geological information. The 26-second pulse offered even greater potential because of its precision and persistence. In theory, scientists could use the signal to study deep crustal structures with extraordinary accuracy over long periods. But one major problem remained. Researchers still did not fully understand what was generating the pulse itself, and that limitation mattered. Using a seismic signal without understanding its source is similar to hearing an engine behind a wall while having no idea what machine is producing the sound. You can study the vibrations, but uncertainty about the mechanism limits how confidently you can interpret the results. That is why solving the mystery became scientifically important far beyond simple curiosity. The pulse was no longer just an unexplained anomaly. It had become a potentially valuable scientific instrument hidden within Earth's own natural motion. Yet even with modern technology, advanced computer modeling and global seismic networks, researchers still could not fully explain why the signal existed. And the deeper scientists investigated, the more uncomfortable the mystery became, because it forced researchers to confront a larger reality. Humanity understands far less about its own planet than most people assume. The deeper scientists investigated the pulse, the more uncomfortable the mystery became. Not because the signal was dangerous, but because it exposed how limited human understanding of Earth still is. Modern civilization often creates the impression that the planet has already been fully explained. Satellites circle Earth continuously. Spacecraft travel beyond the solar system. Artificial intelligence processes enormous scientific datasets in seconds. From the outside, it appears as though humanity has mastered its environment, yet beneath that confidence lies a very different reality. Human beings have explored only a tiny fraction of their own planet. Consider the deepest hole ever drilled into Earth. The Kola super-deep borehole in Russia reached slightly over 12 kilometers beneath the surface before extreme heat and pressure forced the project to stop. That sounds impressive until scale enters the discussion. Earth's center lies approximately 6,371 kilometers below the surface. In other words, humanity has barely penetrated the outer crust. A useful comparison is piercing the skin of an apple with the tip of a needle and claiming to understand the fruit's interior. Fun fact, temperatures at the bottom of the Kola borehole became far hotter than scientists predicted. Rock behaved less like solid stone and more like soft plastic under immense pressure. The oceans reveal similar limitations. Scientists have mapped large portions of Mars and the Moon in greater detail than Earth's deep sea floor. Vast underwater regions remain poorly understood because crushing pressure and darkness make exploration extremely difficult. Against that backdrop, the 26-second pulse becomes more than a geological curiosity. It becomes evidence of a larger truth. Earth is not a solved system. Researchers now suspect the signal may involve processes not fully represented in current models. Some scientists propose unusual standing ocean waves. Others suggest interactions between seafloor geology, atmospheric pressure, and deep crustal structures. A few researchers speculate that multiple systems may overlap together, creating behavior no single mechanism can explain independently. And importantly, none of these possibilities violate science. Uncertainty is not weakness in scientific thinking. It is part of the process itself. A teaching insight matters here. People often imagine science as a collection of final answers. In reality, science functions more like a continuously updated map. Some regions are detailed and precise. Others remain incomplete, blurred, or entirely unexplored. The 26-second pulse exists inside one of those uncertain regions. Researchers can measure it, track it, analyze it, but fully explaining it remains difficult. That difficulty creates an unusual psychological effect. Modern humans are surrounded by advanced technology, yet a repeating vibration beneath the Atlantic Ocean continues without a definitive explanation. Every 26 seconds, year after year, quietly reminding researchers that nature still contains unresolved systems hidden beneath familiar landscapes. And perhaps that is why the mystery attracts so much public fascination. Not because the pulse suggests anything supernatural, but because it challenges a deeply modern assumption, the belief that humanity already understands the world beneath its feet. For now, the most scientifically honest answer remains surprisingly simple. Nobody fully knows what is causing the pulse, and that uncertainty would eventually shape how people outside science began interpreting the phenomenon itself. As the mystery spread beyond scientific journals, the 26-second pulse slowly acquired another identity. People began calling it Earth's heartbeat. From a scientific perspective, the phrase is inaccurate. Earth is not a living organism with blood circulation or a biological heart. The pulse is almost certainly geological or mechanical in origin, and yet the nickname survived, not because of geology, because of psychology. Human beings naturally associate rhythm with life. A repeating pulse suggests continuity, structure, and presence. Long before modern science existed, humans used rhythmic sounds to interpret the world around them. Footsteps signaled movement, drums carried communication across distances, Heartbeats indicated life itself. The human brain is deeply sensitive to patterns, especially repeating ones. That is why the 26-second signal feels strangely personal to many people, despite being nothing more than seismic data on a graph. A teaching insight helps explain this reaction. Humans rarely experience reality as pure information. We interpret unfamiliar phenomena through emotional and symbolic frameworks. When people hear that Earth produces a regular pulse beneath its surface, the mind instinctively searches for familiar meaning, and the closest familiar comparison is biological rhythm. The idea transforms abstract geophysics into something emotionally understandable. In a way, the nickname acts like a bridge between scientific measurement and human imagination. Even researchers sometimes admit the phenomenon carries an unusual psychological effect. The pulse continues while cities sleep, while airplanes cross oceans, while millions of people move through ordinary routines completely unaware that sensitive instruments are recording a repeating vibration beneath the Atlantic Ocean. Fun fact: astronauts observing Earth from orbit often describe an unexpected emotional reaction called the overview effect, a feeling that the planet behaves less like separate countries and more like one connected system. Rhythmic planetary phenomena tend to trigger similar feelings of connection, but there is another reason the heartbeat metaphor persists. Rhythm implies stability. Human hearts maintain predictable cycles because living systems depend on consistency. The Gulf of Guinea pulse displays a similar persistence. Every 26 seconds, again and again, year after year, that repetition creates the unsettling impression that the planet itself is keeping time. Scientifically, of course, the pulse almost certainly results from physical processes involving oceans, geology, or both. But emotionally, the phenomenon touches something deeper. It reminds people that Earth is not static, not silent, not inert. The planet behaves as a dynamic system filled with movement occurring far beyond human awareness. And perhaps that is why public fascination with the mystery became so widespread. The pulse does not merely represent an unsolved scientific problem, it challenges perception itself. Modern civilization often treats Earth as stable background scenery for human activity, but the 26-second signal suggests something different. Beneath cities, beneath oceans, beneath ordinary experience, the planet remains active in ways humanity still does not fully understand. And the most remarkable part may be this: the pulse likely existed long before human beings developed instruments capable of hearing it. Which means for countless generations, Earth may have been keeping this rhythm silently beneath history itself. One of the most unsettling aspects of the 26-second pulse is not where it comes from, it is how long it may have existed. Scientists do not know when the signal began. They only know when humanity first learned how to hear it. The pulse was already active before Jack Oliver detected it in 1962. It existed before modern computers, before digital seismology, and before humanity developed instruments sensitive enough to isolate weak planetary vibrations, and most likely, it existed long before recorded history itself. That possibility changes the scale of the mystery completely. When ancient civilizations built pyramids, temples, and observatories, the pulse may already have been echoing beneath the Atlantic Ocean. When wooden ships crossed unexplored seas centuries ago, the rhythm may have continued unnoticed beneath them. Generation after generation lived and disappeared while the signal repeated silently in the background of the planet. Every 26 seconds, again and again. A teaching insight becomes important here. Human beings naturally measure time through personal experience. Decades feel long, centuries feel ancient. Geology operates very differently. Mountain ranges rise over millions of years. Oceans open and close across enormous spans of time. Entire species appear and vanish, while tectonic plates continue moving slowly beneath continents. Against that scale, human civilization is extraordinarily recent. Fun fact: if Earth's entire history were compressed into a single 24-hour day, modern humans would appear only during the final few seconds before midnight. The pulse belongs to that deeper planetary timeline. It is not simply an anomaly recorded inside laboratories. It may represent an ongoing Earth process operating across timescales far larger than human history, and that realization creates an unusual perspective shift. Most people experience Earth as stable background scenery. Cities, roads, and buildings create the illusion of permanence. But geology tells a different story. Continents drift, magnetic poles shift, mountains erode, coastlines transform. Beneath everyday life, the planet remains active continuously. The 26-second pulse becomes powerful partly because it reveals that hidden activity in a measurable form, not through dramatic disasters, not through volcanic eruptions or earthquakes, but through quiet persistence. Researchers continue refining seismic models and narrowing potential source mechanisms. Instruments become more advanced every year. Data resolution improves constantly, yet the central question remains unresolved. What exactly is maintaining the rhythm? Ocean resonance, volcanic systems, an interaction between multiple planetary processes? For now, no explanation fully accounts for every observation, and perhaps that uncertainty is what makes the phenomenon scientifically valuable. The pulse acts as a reminder that Earth still contains systems humanity does not completely understand. Not because science has failed, but because exploration is unfinished. The signal persists beneath the Atlantic Ocean exactly as it did before humanity recognized its existence. Quiet, regular, patient. And somewhere in the future, another researcher may finally uncover the mechanism hidden behind the rhythm. Until then, every 26 seconds, Earth continues producing another faint seismic beat beneath the surface of history itself. And perhaps the most fascinating part of the story is this. The mystery remains unsolved. After decades of research, improved seismic networks, advanced computer modeling, and global scientific collaboration, no explanation fully accounts for every detail of the 26-second pulse. The ocean theory explains part of the behavior. The volcanic hypothesis explains other parts, but neither theory resolves the entire pattern with complete certainty. That uncertainty is not a weakness of science, it is evidence of how science actually works. Popular culture often presents scientific progress as a straight line moving steadily toward final answers. Reality is far less tidy. Many discoveries begin with confusion, contradictions, and unexplained observations that resist existing models. The 26-second pulse belongs to that category, a signal first noticed almost accidentally, a phenomenon dismissed for years, then rediscovered with better technology, and now studied as one of the strangest unresolved seismic mysteries on Earth. A teaching insight is important here. Science is not defined by certainty, science is defined by method. Researchers observe patterns, test explanations, reject weak evidence, refine theories, and continue questioning assumptions. Some mysteries are solved quickly, others remain open for generations. The pulse may eventually prove ordinary. Perhaps future researchers will discover a previously overlooked interaction between ocean resonance and seafloor geology. Perhaps volcanic systems beneath the Atlantic behave in ways current models cannot yet represent accurately. Or perhaps the signal will reveal entirely new forms of planetary behavior still absent from modern geophysics. History suggests this would not be unusual. Fun fact: for centuries, scientists could observe lightning, but could not fully explain its electrical nature. Entire civilizations witnessed the phenomenon long before physics uncovered the mechanisms behind it. Nature often reveals effects before humanity understands causes, and the Earth has never been silent. Humanity simply lacked the instruments to hear most of its activity. Today, sensitive seismic networks allow researchers to listen to the planet continuously. Beneath the noise of human civilization, Earth vibrates with storms, tides, shifting crust, ocean pressure, and countless hidden motions. Within that enormous planetary symphony, the 26-second pulse continues repeating, quietly, precisely, every 26 seconds. Researchers continue measuring it, they continue debating it, and somewhere in the future, a scientist who has not yet begun their career may finally uncover the missing explanation. That possibility matters, because unresolved mysteries drive scientific progress forward. They force new questions, better instruments, and deeper observation. In many ways, the pulse represents something larger than geology itself. It represents the unfinished nature of human knowledge. Even now, beneath the Atlantic Ocean, a repeating seismic rhythm continues beyond ordinary perception. Not supernatural, not magical, simply unexplained. And perhaps that is what makes the phenomenon so compelling. The existence of one persistent signal reminds humanity that despite satellites, supercomputers and space exploration, the planet beneath our feet still contains hidden systems waiting to be understood. Every 26 seconds, Earth produces another faint pulse, and somewhere, scientists are still listening.